Okay, when is a function differentiable? So a function f is differentiable. That's okay. If the limit by, what's this process called? Do you remember? First principle exists. Good. I.e., if there is a single gradient at a point x equals a, then there's the derivative. One single gradient. The following graphs are not differentiable. Same as like derivative. Okay, graphs with discontinuities. Because obviously there's not a single gradient all the way along the line. There's discontinuity, so there's no derivative. Graphs with sharp points. And the endpoints of a graph. Now, the reason that we can't use the endpoint of a graph, we can't take the derivative of that, is because you got to say that the limit as x approaches a exists, and for that to exist, you got to approach it from both sides and get the same limit. But the endpoint of a graph, you can't approach from both sides; you can only approach from one side. So therefore, the limit as x approaches a doesn't exist for that single endpoint, because you can't approach it from both sides. Okay, our example. Okay, this is our line. It should be joint there. Okay, so is this function differentiable? Sorry? No, that's an x between two lines. It means the absolute value of x. Okay, is this function differentiable at x equals 0?
No.
Why not?
Sharp.
Yeah, it's a sharp point. This bit here is a sharp point. Can you give another explanation why? Thinking about the limit as x approaches 0.
it's not the same. It's from the positive side.
Oh, sorry, as h approaches 0, I should say. So looking at the gradient of the line as x approaches 0.
What are those two things on the other side of x?
Lines,
Oh,
vertical lines.
what do they mean?
They mean the absolute value of x. Don't worry about it too much. You'll learn that later. It's just the function. Think about the gradient of the line as you approach x equals 0 from either side. Is it the same? No. Yeah, it's not the same. So the limit as h approaches 0 for the function does not exist. Because at x equals 0, you get two possible gradients. So at sharp points, that's why you can't differentiate, because you got two different limits, two different gradients.
Wait, is that the same if it's just like one negative, one positive?
Yeah, so at this x equals 0 point, you could have this gradient is positive 1 and this gradient would be negative 1. Okay. This one, f of x and x plus 1 for x greater than or equal to 0 and x less than 0. Think about it. Can we differentiate at x equals 0? Yeah, so differentiate both of them. So f dash x. This one is 2x. This one is 2. Okay, bring the 1 down, minus 1 from the power. And for this one, what is it? 1. Right, so at x equals 0, we're going to sub in x. Sub in, x equals 0 into the first one. What do we get? 2. Sub in x equals 0. What do we get? 1. So they have different gradients at x equals 0, so we can't differentiate. So they got different gradients at x equals 0. Therefore, f of x is not differentiable at x equals 0. Try another one. Got f of x equals x squared plus 2x plus 1 and 2x plus 1 greater than and less than 0. So we know that they're going to meet up at x equals 0. So that's the point we need to test. Do they have the same gradient at that point? So how do we find the gradient? We find the derivative. Derivative of the first one, it's the same as the last question. 2x plus 2. What's the derivative of the second one? 2. So at x equals 0, do they have the same gradient? 2 and 2. They do. So they meet up. So it means that, because this is a parabola on top and this is a linear line, it would be like the parabola kind of coming down and then the linear line coming straight off as a tangent. So the line is continuous. And so approaching x equals 0 from both sides, gives the same gradients. Therefore, f of x is differentiable at x equals 0. Any questions? No? All good. So all you got to do is just at the point where they join up, make sure they've got the same gradient at that point. And then you're pretty good from then on. Okay?